good. There you go. Okay, starting from the front, right? Linear momentum is a product of P and mv. Yep. At home, they will be seeing something strange, right? Because, here you go, right? Product of mass and velocity, right? Which then allow us to write the rest like this, but that is not too important. The key idea is that if your mass is constant, right, dm dt, right, using the product rule, you get d, your m dv dt plus v dm dt. Right? Let me write that out. So you have m dv dt plus v dm dt. Since your mass is constant, this whole bunch goes to 0, right? And dv dt is essentially just a, which allows you to write what you have always done. So it is actually a fallacy to write that. When you say, please state Newton's second law, you write F equals ma. It's actually wrong. Because there are in some situations where the mass is changing. For example, in your rocket, when your rocket is moving forward, its mass is reducing, right? Because it's ejecting fuel backwards. So there are some situations where you need to know which equations to use. Okay, moving on. Oops. So impulse and momentum, knowing F equals to dp dt, if you integrate it in, oh, you are seeing this? Why is it so strange? Wonder what they're saying. And now it's out of shit. And he's gone. Oh my, this guy. Let's try again. While keeping the video going. Also, you have been seeing, okay, so you're seeing this lah. Okay, you're seeing it normally now, but my screen recording will not. This works. Okay, this is done. So if you integrate f in terms of t, right, you actually get this. Integrate dp, integrate f dt, right? You can actually find the total momentum, right? Or rather the change in momentum. Okay. So this is what we call the impulse momentum theorem. Right? Nothing fancy about it. It just means that the impulse given will arrive at a change in momentum. So the change in momentum is possessed by a body, where impulse is provided by a force. Okay? So a magnet acting on a nail, the nail will start to move. The nail will then have momentum. The force of the magnet on the nail, that is where the impulse is given. All right? Try to deconflict the two ideas. Impulse belongs to a force over time, right? And momentum belongs to an object. Okay? Next. That's easy. So impulsive force. So most impulse forces, right, looks like this red shape here. If I were to throw a ball on the ground, it will expect to see a force like this. But in physics, right, it's very hard to describe a force like that. Right? So usually we say there's an average force where the areas are exactly the same. Right? So we approximate this rate force with as if it was experiencing the force in green exerted over the same period of time. Okay, so we say we can approximate that as average force such that the areas are the same. Okay, so there are a lot of fancy equations here, but essentially what they are saying in the math here is that the areas are the same. Okay, questions until this point? Okay. So one is a short duration of time. A, short duration of time but large force. That would be a case of a metal ball on the ground. B would be a soft rubber ball on a very, very soft cushion. Right? You can extend it over long periods of time. So So, a car traveling at 90 kilometers per hour, colliding and coming to complete stop, right? Using what you have just learned here, can you explain to me why cars are designed to crumple? Why cars are designed to crumple? I give you two cars. One car built like a brick, right? Like a brick. You are in the car, it does not crumple. Crumple means the front will fold and flatten. Okay? Not flatten until you, but flatten until where your legs begin. Right? And a car where it does not crumple, which car would you ride? Now with this knowledge, which car would you ride? You ride the crumple car. Why? So that you experience the smaller force. But does that change your momentum? The momentum the change in your momentum will still be the same, because if you're driving at 90 kilometers per hour, 90 kilometers per hour to 0, and your mass is the same, the change in momentum is the same. Right? But experiencing a smaller force might save your life. Okay? Okay, good. Next, momentum versus kinetic energy. All right, so this is an interesting question, right? Two sailboats, A and B, both of mass m and 2m. So A is mass m, B is mass 2m. I think this is not in your notes. Okay. They are both at the start line, and they are subjected to force F until they cross the finishing line. So question part A, which sailboat will reach the finishing line first? When exerted with the same force over time, their momentum will increase, right? The question is, which one will increase its velocity faster? The smaller mass, right? Obviously, it's a smaller mass. So you should see the smaller mass increasing its velocity faster, and hence passing through the finishing line first. Agree? Right, just a short quiz. Now the part B, however, is more fun. Which sailboat has a higher kinetic energy when it crosses the finishing line? Who says A? Who says B? Who says the same? Ready, go. A, B, the same. The same. How do you arrive at that? FD, very good. Because you apply force over the same distance, right? Force and distance, the work you do on the sailboat will become the energy. Hence, they will have the same energy, right? But because the masses are different, the velocities will be different. So which sailboat will have the greater momentum when it crosses the finishing line? What do you think? You can make a calculation of the V, you multiply back with the M. Which one is higher? Or are they the same? All right, who says A? Who says B? Who says the same? Oh, quite a few say it's the same. Let's see if you're right. Okay. So part A we already done, right? The momentums are part A already done, right? The speed of A will be smaller than the speed of B because its velocity is a lot higher. Right? Even without this fancy working, we know that the time of A will be shorter. But this is one of the ways to present it, right? The acceleration of A is twice the acceleration of B. Right? So naturally, it will cover a larger distance in a shorter time. Okay? From this equation. Part B, we asked how their momentums would be like. Of course, how their energies would be like. But the answer here seems to be, oh yeah, kinetic energy, right, is the force times distance, right? So the force is the same, the distance is the same, right? It will be the same, right? No problem. K refers to kinetic energy of A and kinetic energy of B. Part C, let's look at it. Which one will have the highest momentum? So force times time, force times time. What do you think? With this now, does it help you? This is the hint. And the answer is B. Yeah, that's right. Because B, right, is the longer time, is subject to a longer time. You have a larger momentum, right, when it crosses the finishing line. So this is the very good slide to differentiate. I'll send you the slides at the end, right? To differentiate between, this is a very good question to differentiate between momentum, kinetic energy, and time. Conservation of linear momentum. So this is the key word. If there are no external forces acting on an isolated system of particles, not just one particle, the rate of change of momentum will be 0. Okay? So the sum of momentum will be constant, which means the initial momentum will equal to the final momentum. So just fanciful Greek letters, but the idea is easy. The sum of the initial momentums of all the particles is equal to the sum of momentum of all the particles at the end. So for example, if you look at our solar system, right, and assume that there are no other planets and galaxies and dark holes or whatever out there, the momentum of our solar system should stay the same over a long period of time. But when I say momentum, I'm not talking about the momentum of just Earth. Earth's momentum will change, but the momentum of all the planets involved, considered, will not change. Alright, so here we proceed on to a simpler case of collision of particles. Right, so the total momentum of an isolated system just before collision equals to the momentum after that, yeah? Pretty direct. So when you have collisions, you can ask whether the collisions are elastic or not. So let me give an example. If I drop a ping pong ball on the floor, what do you hear? Yeah. If you hear that sound, is that a sound energy? Yes. If there's sound energy, the rebound of the ping pong ball does not go to as high as before because sound energy is also in terms of sound, heat, and colliding with the ground, right? So that is what we call an inelastic collision, right? There are very few elastic collisions that we know of at our scale, right? I remember when I was young, I was given a super bouncy rubber ball. The one that have you all played with that before? Where you throw very hard, then it bounces on the ground, hits the roof, and comes back down again. And it keeps bouncing for a while. Right? But even then, it doesn't go on forever. Right? What is a possible elastic collision? Well, actually, elastic collisions happen at the atomic scale, right? When you have particles colliding with particles. Okay, and sometimes actually the collision is not actually a physical collision, but the charges repelling each other. Okay, you will learn about that later. Anyway, work, energy, power. So we have finished dynamics. Moving on to work, energy, power. Next topic. Wow. Okay, work and energy we know. Force and distance is work. Energy is just a concept of a quantity possessed by the object. Okay. There are many forms of energy. You can learn about that later on. In fact, I will be a lecturer for that, so don't worry about that. Weightlifter, if he moves it up, yeah, there's a force. Moving down. Okay, come, work done. In the first picture, what is the work done by the weightlifter? Is it positive or negative? It is positive because the force is upwards, and the displacement of the weight is upwards, right? So the work done by the weightlifter on the object is positive. In this case, when he holds it there, the displacement of the weight is 0. Is that work done by the weightlifter? No. Okay, so I ask you this question. If there's no work done by the weightlifter, there's no energy used, no energy given to the weight, right? But why does it feel so heavy to carry something heavy for a long period of time? Why does it feel so tiring to do that? Right, think about that. Okay, think about that. I'm not going to give you an easy answer. In this case, when he's lowering it down, he's still exerting upward force because he has to, right? He has to lower it down slowly. If he's lowering it down, accelerating downwards faster, he will probably hit his leg, right? So he's lowering it down slowly. He's still exerting upward force, but the displacement downwards, the work done is negative. So if you look at these three pictures, right? Here, the work done by the weightlifter goes towards the gravitational potential energy of the weight. So it's doing positive work, makes sense. Positive work gives positive energy to the external system. Not doing any work doesn't give any additional energy to the system. Here, doing negative work, right, means the object is losing energy. The GP of the weight before and after has decreased. Alright, moving on. So there's a work done for GP. How does work done relate to gravitational potential energy, and how does work done relate to kinetic energy? In fact, you need to derive these equations. You derive mgh and half mv squared for the concepts of work later on. Right, I'll be teaching you that soon. So I'm just going to move on very quickly. So if you have a variable force, how do we do it is that we approximate it. Right, we see a variable force here over a certain distance. We approximate it with rectangles. And we say that if delta x becomes 0, then we can say that the work, right, is the integral of f dx over the limits of x2 over here and x1 over here. That's right. It's the area under curve. Yeah. So you will see quite a few force distance graphs, right? Be it the force fx graph of a spring or fx graph of gravitation, right? For gravity, forces on the planet, forces on charges, between charges, with respect to distances. So you must know that the area under it will be the work done. Right? You must really do the mental switch from the graph to make that link. Right, here we go. First example, right, of work done on spring. If you pull the spring, right, Hooke's law states that the force is proportional to the extension. So if you extend a spring by 1 meter, and you feel a force of 10 newtons, you require a force of 10 newtons. To pull it, to extend by 2 meters, you need a force of 20 newtons, which explains why it's a straight line now of F versus X. So the gradient in this kind of graph will be K, which is what we call a spring constant. The spring constant is also called a measurement of stiffness. So the larger the K, the more stiff the spring, the larger the force you need to exert to extend it by a little. Okay. So work done is the area under it over here. Not a big problem, right? Just f dx and equate. You can actually prove this equation or derive it out. No problem. And the change, let's say you extend it to this height where my arrow is. If you extend it further, it's actually a parallelogram, right? But simply say it's actually the area of one larger triangle minus the area of a smaller triangle over here, which is explained by this equation. Okay? Right? Work energy theorem is actually how you derive your half mv squared. So if I push, okay, am I going too fast? I mean, okay. Hand, okay. Sorry, trapezium. Trapezium, right? If you extend it to this side, it will be a trapezium, sorry. Right, trapezium. Right, we'll achieve power theorem. So if I push a box, right, on the ground, and assuming there's no friction, I push it with force of 10 newtons for 10 meters, I've exerted 100 joules of energy. The 100 joules of energy will become the K of the box if there's no friction. Did I raise the box up? No, so there's no GP. So work done is equals to KE. And that's how you derive it. So here you have work done is force times distance. Force is mass times acceleration. The acceleration is the final velocity minus the initial velocity divided by time. Distance moved is half of the initial velocity plus the final velocity times time. Can follow me until now? Okay. Put all this together, you get this huge monster. You simplify, you get half mv square minus half mv square. Okay. It's just like that. Okay. There is a simpler derivation. If you look at this, instead of using these two equations, right, you can actually use this. Have you learned the equation v squared equals to u squared plus 2as? I believe you have. If you rearrange this monster, you get your s is your d, you suck this thing into here, your a will cancel out straight away. And this equation actually appears almost immediately. So actually this is a faster way to derive the work energy theorem. Okay? This equation is actually the faster way to derive this theorem. Oops. Now I got to erase this, I think. How do I erase this? Erase. Right. Okay. So the work energy theorem actually states that the work done by external force in moving object from x to y is given by that. Allow you to do all this, and then hence that. So the net work done on the particle equals the change it can actually done. It just sounds cool and difficult, but it's actually really simple and not cool. Okay, quite cool, still quite cool, but simple. Okay. All right. Self-explanatory, right? KNG is given half mv squared. Work done by is a change in KNG. Right, finally here, forces on a hammerhead, right? In the power driver. Do you know what a power driver is? Yes, right? It's like a souped up version of a hammer, right? A very good hammer. Yeah. Should I show you the video? Okay, so sorry to the guys at home, you won't be seeing this because I want to show them a video.